again. Okay, the key thing in terms of improving the pregnancy rate, particularly if we are undergoing pre-implantation genetic testing, where we have a 5 to 6 day embryo and we can biopsy that and then do the genetic test to determine whether or not the mutation that we're trying to avoid is or is not there. So it's easier said than done that we can determine exactly the best accuracy for pre-implantation genetic testing. So for about 20 years, look at the first slide, IVF for fluorescent in situ hybridization simply was not very effective, and we had to abandon that. 2010, we had really the first effective single gene testing to determine the genetic basis of the embryo that could be transferred. And in that particular area, believe it or not, we had a remarkable increased frequency of pre-implantation genetic testing had been done by the best at the time, which was array CGH. That simply means that you have DNA from multiple chromosomes that are looked at, and you could then deduce what happens if there is too many or too few chromosomes. Perfect common sense. So here's a 2012 paper that was done. You see here, these are implantation rates for individuals and centers in which they had only a limited number of individuals. So this was, you didn't have outside individuals contributing. Each of these were a single entity. And you can look and see the controls without a biopsy, you can see are about 20% less effective than pre-implantation genetic testing. Now, the real issue, however, is not the indication, the center itself, but the single embryo, because the patients are coming to us and they want to know whether we can do the right thing in terms of telling them whether the embryo that's going to be transferred is or is not what they want. So it's the same thing as any test you would get for disorders or so. So here you have a predictive value. The bottom line you say is we are going to transfer this embryo and therefore compare the intake of euploid versus aneuploid embryo. But in doing so, we're not going to tell you the diagnosis that has been transferred because that biases the sample. And so this is what's done. You do a biopsy of the embryo and measure the amount of DNA per chromosomes, but you do non-selection. You transfer it and you don't find out the answer to the chromosomes until about 13 weeks later during pregnancy. So that's the basis of thing. So if you use that array CGH, in 2012, this is Richard Scott, a United States star in this particular area. And so they did that. They transferred the embryo. They didn't know the results until about 13 weeks later. And at this time, there were 99 aneuploid embryos and 133 euploid embryos. The aneuploid embryos had a 4% pregnancy rate, and the euploid embryos had a 42% pregnancy rate. So no question that if aneuploid is not as effective as euploid, there are still some people who believe that that could be true, but the data certainly are not there. Now, you still had a problem. Let me go back to show you that slide. The 4%, that's not what we want. We don't want to transfer an embryo with a 4% likelihood that's going to be a take and it's going to be there forever. So along came another mousetrap, and this was next generation sequencing, 2021, and it's the same group that we mentioned before. Don't need to tell their names again. And in here, look at the two lines because they're very critical. Euploid, 82% of the transferred euploids implant, 71% clinical pregnancies, and 60% take-home baby. Excellent. For aneuploid embryos, however, it's not so good. Surprisingly, you do have about 40% implantation rate. You have a reasonable clinical pregnancy rate of about 23%, but the delivery rate is 0. So unlike the 4% that we had before, which is probably due to mosaicism, this is a different story or so. Now, the star of the story is next generation sequencing. We don't have time to go over in great details, but you can look at how it's very easy to schedule and see that you have a diploid embryo for each of the chromosomes here, and we don't have a trisomy, we don't have a monosomy. You can see how they look in the second and the third next generation sequencing. You know, in the red one in the middle, you are missing a chromosome 16. At the top, you have a trisomy. So these are easy to see, and they're not so simple to understand the basis, but this works. Now, the punchline, as I said before, is that you get a lot of pregnancies if you keep trying. So this is what happened to the Scott group that I just told you about. Here's the design. You can look at it. 4,429 women who underwent up to 3 cycles, successive cycles. So look at the results. Mean age 35. The first transfer resulted in a 70%, 69.9% sustained pregnancy with the delivery of almost the same 64%. If it didn't work, it used to be we'd say, well, that's too bad. Let's see what the problem is. Instead, what this group did was it's still a good-looking PGT-A normal embryo. Let's transfer it again. 59.8%, 54% take-home baby rate. If it didn't work the second time, do it the third time, and you could read that column there. The bottom line is, at the end of the day, 92% of women who wanted a baby to take home get a baby. They just don't get it the first try. You come back the next try. So this is something that really is a game changer. Now, what happens actually to the euploid and aneuploid embryo? You can see the euploid at the top. They start at almost 90%, and they slowly go down a little bit. I don't think I have a pointer here, but you can read that just as well as I can. And this is a great success rate for these individual embryos. An aneuploid starts out with not too disappointing. It looks like about 40% of these actually implant, but at the end of the day, you have 0 take-home baby rates. So to me, it couldn't get more clear in terms of doing that. Just to briefly say, there's another reason to do single embryo transfer. To the left and the right are an excellent study done by Foreman in the United States. The red represents a PGT-A cycle embryo, and the yellow represents no transfer. But in fact, two embryos are transplanted at the same time. So if you look to your right as you move forward there, you see that the success rate for a single embryo is off the board for euploid transfer. However, if you look at the same thing and to see what happened to the singleton embryos and to the singleton deliveries that are in yellow, that it's the same amount, about 50%. So 50. So the bottom line there is that the take-home baby rate, if you do twins and you don't test it, what you're going to wind up is that half of your cycles are going to be twins. So 27% of the cycles were twins for untested embryos, and for singleton embryos, it was the opposite. They were all singletons, so that's what we like. Now, we have another issue that occurs in the general population that we're looking at, and that is the question that I've posed. Why does not every PGTA euploid embryo result in a pregnancy? Why not? You know, so, and even in excellent hands, as I've just outlined, for United States investigators, you have to start somewhere. And the best centers that usually have about 60% take-home baby rate, you know, don't have 100% until we repeat the cycles. So why does not every PGTA euploid embryo result in a pregnancy? So skip down just a little bit. The second bold-faced is structural chromosomal abnormalities are missed, you know, and in those particular situations, it would be a reciprocal or Robertsonian translocation, so you'd have an abnormal embryo, and you would like not to have that to begin with. Then you have all of these autosomal abnormalities that we're familiar with, and we have told our medical students about that for decades or so. And here they all exist: poorly controlled diabetes, hypotension, antiphospholipid antibodies in the second trimester. The problem is that we've overrated them. We've assumed that they've explained every PGTA embryo that has been transferred, and in that particular case, that's simply not the case. It's lower. So the two things that I think are worth take-home rate as we look about it is, number one, stochastic implantation. Stochastic is a good English word that basically says bad luck. You know, you have transferred it and you thought it was going to work and it didn't work. And so in this case, it's probably the failure to put the embryo, the 5 to 6 day embryo, near the endometrial receptor. And so, but there's not a green light at the time that you've transferred that, and you really don't know whether or not it's accurate or not. So, and then the other issue is mosaic embryos. And this is a key issue, and it can be resolved really fairly quickly, and again, increase the take-home baby rate. So here is a drawing of individuals who may confront an embryo that's mosaic. So the greens represent a euploid, and the reds represent aneuploids. So this is pretty clear. When you biopsy a 6-day embryo, you get about 3 cells. So you really don't have a lot to work with at that particular time. If you look at certain of these embryos, for example, let's look at the 1, 2, 3, the third down, and this is an embryo that has a red spots in them, and that particular is for the cell, the inner cell mass at that stage. So then if you biopsy this and you biopsy the circular aneuploids, the circular normal cells, you would say this is normal, but it doesn't have, it's not going to be normal at the inner cell mass. So the bottom line is that there is limitations in what one can do when you do a transectoderm biopsy, around here, and that's going to show up later in the cell cycle. Now here's where we are right now. Chromosomal abnormalities are detected by next generation sequencing. I've told you that that's the best that we have to offer, and it's probably not going to get much better. So you can look at the blue, the red, and the orange, and you can add this up, 44, 13, trisomy. This is what you would ordinarily expect. But in reality, what you expect is the green, purple, and yellow, and these are different embryos, and these are mosaic. They're not a single chromosomal analysis that plays in the entire cycle or so. So some of these are really worth remembering because we can get a better mousetrap in this area than others. For example, the best one is segmental chromosomal mosaicism. You may or may not have heard of that, but this is a situation in which, unlike most other mosaic embryos, it's not related to maternal age. So that means it is unlike whole chromosome mosaicism that we've grown up through the decades, many, many decades in my life, and just a few for some of you in this room. But the key thing is you get a certain amount for certain chromosomes. The bottom line is that the cell cycle has not allowed completion of the correction. So you have DNA repair that's essential to keep the ovaries in place, because they're going to be remain there for decades, and you're going to have cell cycle checkpoints. So if you remember your cell cycle checkpoints, you come around, can you continue to the next step in the circular pathway? If so, yes, and if not, abort that particular embryo, because it's going to result in bad news. So this is what's known. Now, remember before we looked at segmental chromosomal mosaicism? Look at here is where the chromosomes that are involved in segmental mosaicism are. And you notice that the big ones are to the left. So that's that is the largest chromosomes. Just look down 1 through 5 and you can see much bigger than, say, the other end where they're smaller. So what this means is common sense. If you've got a big chromosome, it's taking you longer to go through the cycle than if it's not a chromosome. It's not a big chromosome. And so we look, if we are going to transfer a mosaic embryo for a mosaic embryo, again, it's going to be a segmental chromosomal mosaicism. Now, where do we stand right now? So basically, since we can tell whether there is a segmental translocation and we can give an idea about what we need, we have developed plans in which the mosaic embryos can be developed into healthy newborns, and it depends upon the percent of euploid embryos that are in that embryo. So Greco did this first in 2015, along with a series of other investigators, mostly in Europe, that came along with the idea of the implantation rate. You know, the numbers are all over the place here, and it's, the bottom line is that it works. You did not need to avoid the implantation of mosaic embryos. Let's just see what made them better. And what made them better is this. If you look at the percent aneuploid embryos, and your embryo is less than 20%, we now know that 20% aneuploid DNA is not going to interfere with success. On the other hand, if it's greater than 80%, in this case aneuploid, it's almost zero implantation rate. So yes, you can still have a good baby if you have at least 20% mosaic embryo, 20% euploid that manifest as mosaic. If you have a little more, 50 to 80%, you're still a mosaic, but it's less favorable because of the common sense that you would expect. You have lower pregnancy rates and you have higher miscarriage rates. So we prefer that the number of aneuploid embryos is certainly no greater than 50%, but on the other hand, we may find ways in the future that even that results. What clearly does not work is the 80% aneuploid rate. You can wonder why we were messing with the 20%. The bottom line is that there's no embryo that is completely aneuploid or completely euploid. And the embryos have lived with that. There's all sorts of correction factors that we don't need to go into, but that's the way it really works. Now, just the final two slides show you, people said, well, we've got it, but why don't we go ahead and have large samples? So this is the first 100 mosaic embryos that are transferred. You can see that the bottom lines, so that 80% of these made it through, and that's the pregnancy rate that tends to occur from that. So you can see here at the bottom line, 79% did well, 20% did not, but of those 79%, the large number came in successfully. So the bottom line, to take home message, don't stop with the single embryo. Transfer another PGD-A embryo a second time, a third time, and data exists, although I didn't show it here, for up to 5 cycles. So the bottom line is that this is a huge success rate that we need to implement. The final slide shows you the Preimplantation Genetic Diagnosis International Society. For the last 2 cycles, they've been the same. We recommend transferring the euploid embryo if you have one, and if not, let's try to get the best mosaic embryo that exists, and so that would be those with less than 20% aneuploidy. And if there's no embryo that is euploid, transfer mosaic embryos with 20 to 50% aneuploid DNA. And the final take-home message is that if you're counseling the patients, the miscarriage rate is higher, the implantation rate is lower compared to embryos that have less than 20% aneuploid DNA. So we made it through a strange start for the sample, but I'd like to thank you for the opportunity of covering this.